All right, let's jump right in. Have you ever really thought about how the internet works? I don't mean the cables under the ocean or the router in your house. I mean the scale of it, the sheer mind-boggling scale. How can it possibly handle everything we throw at it every single second of every day? Well, we're going to dive into that because the answer is, frankly, one of the most incredible engineering feats of our time. And it all boils down to one simple question.
Seriously, just stop and think about that for a second. Right now, as you're listening to this, millions of people are binge-watching their favorite show, millions are adding things to their Amazon cart, and billions, with a B, of Google searches are flying across the web. How does it not all just, crumble? What's the secret sauce, the invisible architecture that keeps this whole digital world running so smoothly?
So the heart of the problem really is scale. And I'm not talking about your local pizza place's website getting a few thousand hits. No. We are talking about global services that have to deal with these massive, totally unpredictable waves of traffic, and they can't even have a single hiccup. The old ways of building things, traditional computing, it just wasn't designed for this, not even close.
And that's where the solution comes in. It's got a name, and you've probably heard it, the Hyperscale Cloud. This is the architectural marvel that's running behind the scenes of almost every major digital service you touch. It is literally the engine that powers our modern internet.
Okay, so what is it really? Well, at its core, a hyperscale environment is a type of cloud architecture that was built from the very beginning with one thing in mind: growth. And not just steady growth. I'm talking about the ability to expand and shrink its resources, its computing power, almost instantly. It's like a lung that can breathe in or out on a massive, global scale, perfectly matching whatever demand is thrown at it.
Let's break down its core characteristics. And what's cool is how they all fit together. First up, massive scale. We are talking about thousands, sometimes millions of servers all over the world. Because they're spread out or distributed, it gives them this incredible elasticity. That's the magic word right there, the power to stretch and shrink computing resources in real time. And the foundation for all this? Modular hardware. Think of them like standardized Lego bricks. Easy to pop in, easy to pop out, which makes scaling up or replacing parts super fast.
But it's not just about being big, it's also about being smart. In fact, hyperscale systems are built with a really interesting philosophy. They are designed to fail. That sounds weird, right? But they fully expect that servers will break. So they build in all these layers of redundancy and automatic failover systems. One server could literally go offline and you, the user, would never, ever know. And the secret ingredient making this all happen? You guessed it, automation. Pretty much everything, from launching new features to keeping an eye on the system's health, is handled by software. This cuts down on human error and keeps things running 24/7.
Okay, so to really get a feel for why hyperscale is such a big deal, it really helps to put it side by side with the traditional cloud setups that came before it. Because the difference isn't just about being bigger, it's a completely different way of thinking about computing.
And this chart here just lays it all out. Look at the scale row. You've got hyperscale with millions of servers globally versus a traditional cloud which might just have one or a few data centers in a region. Huge difference. Now look at elasticity. Hyperscale is all about that dynamic, real-time scaling. Traditional clouds, much more manual, you have to plan for it. And it all comes down to the architecture. Hyperscale is distributed and automated. Traditional is centralized and manual. The end result of all this is something called economies of scale, which basically just means it makes all this computing power way cheaper and available to everyone.
All right, so we get what it is and why it's so different. But the really juicy question is, how do you actually build one of these things? What's the secret recipe? Let's take a look at the design blueprint.
It really comes down to 4 key pillars. First, you've got microservices. Instead of building one massive, clunky application, you break it down into tiny, independent little services. So on a shopping site, the search bar is one service, the cart is another, the recommendations are another. See? This means if a ton of people are searching at once, you only need to scale up the search service, not the whole site. Which brings us to pillar 2, horizontal scaling. This just means when you need more power, you add more servers, not a bigger server. It's way cheaper and more flexible. And the magic that manages all this? Total automation, through something called infrastructure as code. It's exactly what it sounds like. You write code that defines your entire setup, like a blueprint, which makes everything predictable and super fast to roll out.
Okay, now that 4th pillar we mentioned, statelessness. This one is a huge deal. It's maybe the most important concept to grasp here. It's a simple idea, but it's totally profound. You design every service so that it doesn't hold on to any user information. It has no state, no memory of who you are or what you just did. Now, why on earth would you do that?
Well, because it makes every single server completely interchangeable, like a generic cog in a giant machine.
So, where does your info go? Well, as the source material puts it, the state, the stuff that needs to be remembered, like what's in your shopping cart, is managed somewhere else entirely. It's stored in a separate, shared database that any server can access. And this is the key. It means any server can handle your request at any time. This is what makes things like load balancing and instant failover possible. If the server you're talking to suddenly dies, your next click just gets sent to a different, healthy server, which pulls your card info from that shared database and carries on like nothing ever happened. Brilliant, right?
Okay, so this is all really cool tech stuff, I get it. But let's bring it back down to earth. Why does any of this actually matter? What's the real-world impact? Well, in a word, innovation. This architecture is what makes modern innovation possible.
For any business, the benefits are just massive. You can suddenly handle a huge rush of customers without your site melting down. You only pay for what you use, which is a game changer for costs. And maybe most importantly, Hyperscale is the bedrock for the next wave of tech. I'm talking about the huge, power-hungry demands of AI, machine learning, and crunching massive amounts of data. Honestly, these fields just wouldn't be where they are today without this kind of power.
And who are the big players building all this? Well, you definitely know their names. We're talking about the giants: Amazon Web Services, or AWS, Microsoft Azure, and the Google Cloud Platform. You can think of them as the landlords of the modern internet. They own the property, and everyone else, from the tiniest startup to a huge corporation, just rents space to build their businesses.
So there you have it. Hyperscale architecture is the invisible engine that makes our digital world go round. But with things like AI and the Internet of Things just exploding, the demand for data and pure processing power is going through the roof. It really leaves you with a fascinating question, doesn't it? What comes after hyperscale? What's the next great architectural leap that's going to be needed to power the world of tomorrow?